In this video, we're going to do another example of a Lewis structure. I want you to try this out yourself and then check your work after. We're going to draw the ozone molecule. And so ozone is a molecule made up of 3 oxygen atoms connected together. And we're going to follow the same process that we typically do. We're going to do our valence electrons. So there's oxygen group 16, so 6 valence electrons, but there's 3 oxygens. So that's 18 valence electrons a place. And it's pretty easy to come up with a central atom because they're all the same atoms in this case. So we're just going to put O, O, and O, and we're going to connect them together with single bonds. When we do that, that means we used up 4 electrons, so minus 4 there, and that's left with 14 valence electrons, and we can start filling them up in our structure here overall until everybody's happy. So this will be 1, 2, 3, 4, 5, 6, 7, 8, that's happy. So that's minus 6. Now we're down to 8 valence electrons left to place. And then 1, 2, 3, 4, 5, 6. And plus the bonds in there. So now that's happy. So we place 6. And we now have 2 left to place. And we can put them on the central oxygen atom here. And now we're down to 0. So we placed all our electrons. And we have to see if everyone's happy. And as you can see, all the oxygens are pretty happy, except for the one in the middle. The one in the middle still needs another set of electrons to help it complete its octet. Oxygen's not one of the ones that can have an expanded octet. It's not one of the ones that can have an incomplete octet either. It needs to have a nice stable octet. So we can ask one of the oxygens to help and provide some electrons in a bond. So perhaps the oxygen on the right side can do that and put these electrons into a double bond. So we'll do that. So 1, 2, 3, 4, 5, 6, like this over here. And now that oxygen's happy. However, you'll notice that the oxygen on the right didn't have to help out. It could have been the oxygen on the left. So let's see what that situation would have looked like instead. Not in addition to, but instead. Because if we put 2 double bonds in there, now our oxygen will have an expanded octet. It'll look something like this. So this is wrong. I'm just going to show you. Our oxygen in the middle would have an expanded octet, which could not happen, right? You'd have 8, 10. Can't happen because oxygen's in period 2. So that wouldn't work out. So instead of that, we could say this oxygen helped. And that would look like this. So these are 2 equivalent structures. They're basically the exact same, just the electrons are in different locations. The double bonds are in different locations, but they're the exact same thing essentially. And so what we've done here is we've drawn what's called resonance structures, and we can put those 2 arrows there to show that. Now, the arrow with the 2 heads does not mean that the 2 structures are interchanging or are becoming one and the other over and over again. What it means is that overall the real structure is a hybrid of the 2. So when you have resonance structures, it doesn't mean that you have a mixture of all these structures existing independently. It means the actual structure is some hybrid of these. And so the actual structure, we'll often call it a resonance hybrid. A resonance hybrid. So again, it's a hybrid of those structures, similar to what we saw with the carbonate ion. So when you are drawing, if you do see that there's a possibility of having resonance structures that are really equivalent in this way, same bonding order, just double bonds in a different way, almost as if you rotated the molecule, it would become the other one, then you have resonance structures, and as a result, the actual structure is a hybrid somewhere in between the contributing structures. So each of these resonance structures we drew is called a contributing structure. It contributes to the overall hybrid, to the overall resonance hybrid. So contributing structure. So when we did carbonate, there were 3 contributing structures that contributed to the resonance hybrids. There may be others that you can draw that are a little bit different from these ones here, but they don't contribute as much to the resonance hybrid. In the next video, we're going to take a look at our final concept called formal charges, because there are some cases where sometimes two structures look like they're possible and they follow all the rules, but one might be preferred over the other. And to determine which one's preferred, we can use a concept called formal charges.